Welcome to this explainer. Today we're diving into, pun absolutely intended, the physics of floating and sinking, specifically unlocking Archimedes' principle. We're going to look at why certain things just plummet straight to the ocean floor, while others, effortlessly float right on top. It's all about unpacking how density impacts floating versus sinking, with some pretty wild examples along the way. So, to kick things off, why do your arms feel strangely heavy when you step out of a warm bath? I want you to picture that familiar sensation. You're lounging in the tub, relaxing, and then you lift your arms out of the water. Suddenly, they feel strangely, almost uncomfortably heavy, right? Why is that? What literally changes the exact second your skin breaks the surface? Well, this everyday experience is kind of our central mystery for today, and solving it means understanding the invisible support system you just left behind in the water. But before we can solve that, we've got to bust a major middle school misconception. We've all heard the rule, heavy objects sink and light objects float, right? Well, actually, scratch that. Weight alone doesn't decide an object's fate in the water. The real mechanics at play are a whole lot more complex and, honestly, way more elegant than just heavy goes down, light stays up. Archimedes' upward push.
Okay, back to the bathtub. The real reason your arms feel lighter underwater is because of something physicists call buoyant force. This is the net upward force exerted on literally any object immersed in any fluid. So where's this magical push coming from? It boils down to pressure. See, in any fluid, pressure increases the deeper you go. Because the bottom of a submerged object is always deeper than its top, the water pressure pushing up on the bottom is always strictly greater than the water pressure pushing down on the top. And that difference, that creates a net upward push. It's always happening, whether the object is floating, sinking, or just hovering somewhere in the middle.
Now, the actual mechanics of this were cracked a really long time ago. Think of it in 3 steps. First, an object enters a fluid. Second, because two things can't occupy the exact same space, the fluid gets pushed out of the way, or displaced. And third, the upward force pushing back on the object ends up perfectly equaling the weight of that displaced fluid. This whole concept is a massive tribute to the ancient Greek mathematician Archimedes. The story goes that he realized this while sitting in the public baths and was so pumped up that he ran naked through the streets of Syracuse yelling, "Eureka!" which, translates to, "I have found it." So the crucial takeaway here is what we now call Archimedes' principle. The buoyant force on an object equals the weight of the fluid it displaces. I really want to emphasize this because it's the foundation for everything else we're going to talk about today. The upward push your body gets in the water depends entirely on the weight of the water your body shoves out of the way. It's got absolutely nothing to do with your actual weight. Basically, it's a tug-of-war between your weight pulling you down and the displaced water's weight pushing you up. Density, the floating factor. Now, the ultimate tiebreaker in that tug-of-war between gravity and buoyant force is density, represented in physics by the Greek letter rho. Density is just the average mass per unit volume of a substance. Basically, it's a measure of how tightly packed the matter is inside an object. And this right here is the secret code. Density dictates exactly if the buoyant force generated by displacing a fluid is going to be strong enough to overcome an object's own weight. To put that into perspective, let's look at some real numbers. We measure density in kilograms per cubic meter. Liquid water sits at exactly 1,000. But ice is 917. Because ice is less dense than liquid water, it floats. Simple enough, right? But then look at seawater. It's denser than fresh water, sitting at 1,030. Because seawater is denser, a specific volume of it literally weighs more. So the buoyant force it applies is actually stronger. That's exactly why you, or any object, will float noticeably higher in the ocean than you would in a freshwater lake. Okay, so we can now establish the absolute, hard and fast rules of buoyancy based on density. If an object is denser than the fluid around it, it has more mass crammed into the same amount of space than the fluid does. So its weight is going to beat the buoyant force, and boom, it sinks. Conversely, if the object's average density is less than the fluid's density, it floats. This is the core dynamic of how density impacts floating versus sinking. Shape, volume, and ships. So, knowing these strict rules, humans have engineered some absolutely incredible workarounds. Which brings us to a massive puzzle. How does a 10,000 metric ton solid steel ship actually float? Especially when steel is way denser than water. Steel is nearly 8 times the density of water. By the rules we literally just established, a massive chunk of steel should go straight to the bottom of the ocean.
Yet gigantic ocean liners cross the globe every single day. So, no way, right? How is that even possible?
Well, it brilliantly comes down to shape and average density. Think about a solid lump of clay. If you drop it into a bucket of water, it sinks instantly. But if you take that exact same lump of clay, meaning the total mass hasn't changed at all, and mold it into the shape of a hollow boat, suddenly it floats. By shaping it into a boat, you drastically increase the overall volume it takes up without adding a single ounce of mass. And that's exactly what engineers do with ships. When they shape steel into a massive hollow hull, they're trapping a huge amount of air inside. And air has a super low density, so the average density of the whole shebang, the steel hull, plus all that trapped air, becomes significantly less than the density of water. By increasing the volume, the ship ends up displacing a ridiculous amount of water. We're talking about a standard cargo ship displacing around 100,000 million kilograms of water. That provides a maximum buoyant force that's 10 times the actual weight of the steel, making it float and letting it carry a massive amount of cargo. It's just brilliant engineering.
The fraction submerged. All right, so we know why things float, but did you know we can also predict exactly how they're going to float? When something floats, it doesn't just sit perfectly on top of the water. A specific portion rests below the surface, and we can calculate exactly what that proportion is using specific gravity, which is essentially a simple math cheat code. The fraction of the object that gets submerged is perfectly equal to the average density of the object divided by the density of the fluid.
Let's look at a real-world human example from our sources. Say you've got a 60-kilogram woman floating in fresh water, and her lungs are full of air. Her average body density is about 970 kilograms per cubic meter. Since fresh water sits right at 1,000, we just divide 970 by 1,000, and the math flawlessly dictates that exactly 97% of her body volume is going to rest below the water's surface, leaving just 3% floating above. It's literally that exact. And manipulating or measuring density through Archimedes' principle isn't just a neat trick for pool parties. It solves real complex problems every single day. For instance, submarines use ballast tanks to take in or pump out water, actively changing their average density so they can float, sink, or hover whenever they want. Mechanics use floating hydrometers to measure the specific gravity of battery acid to check its health. Medical pros use underwater weighing to determine human body density, giving them incredibly accurate measurements of percent body fat. And historians, they actually use this to authenticate ancient silver coins by measuring their apparent weight loss in water to calculate density, pretty much exactly what Archimedes supposedly did for the king of Syracuse's crown.
To wrap things up, I want to leave you with a final, kind of mind-bending question. If less dense materials float on denser fluids, like icebergs in the ocean or, hot wax in a lava lamp, are solid mountains floating on the Earth's mantle right now? Remember, fluid mechanics applies to anything that yields and flows. Over long periods of time, the Earth's mantle actually has fluid characteristics. Geological measurements show that massive solid mountain ranges have a lower density than the dense mantle rock beneath them. So based on the exact same physics that floats a steel ship, are the solid mountains you hike on literally floating on the fluid Earth below? Well, it turns out, yes, they absolutely are. Thanks for joining me on this explainer, and keep exploring the incredible physics of our world.